Welcome to the Smart Living Spaces vlog. I am Sharon, architectural and passive house designer. I'm also a homestay professional located here in New Zealand. It's my mission to make healthy, comfortable, energy efficient and affordable homes for everyday people. So come on a journey with me where I share my knowledge gained over the last couple of decades, because we aren't going to be building better if people don't understand and see the value in changing what we are creating. So hi guys, welcome to this is March's vlog. So last month I covered the 7 gaps in the New Zealand Building Code, and this month I am highlighting how Passive House actually fills those gaps, and next month I'll be highlighting how Homestar fills those gaps, just so that you can understand where the assumptions are with a code-compliant home, because remember that a code-compliant home built to the New Zealand Building Code is a legal one. So it's a legal document. All building work has to comply with the New Zealand Building Code, and it impacts on the ability of that house to be sold. You can't sell an illegal home, insure, and also banks won't lend on illegal building work. So it's a really good thing to be clear about what is actually a quality and a healthy and a good performing home versus just the mandatory minimums that it needs to meet. Because a lot of people banter around that their homes is code compliant, and almost boast about the fact that that's a sign of quality when it's in fact not. So just to recap on what I covered last month, I recapped on the differences in terms of ventilation, energy efficiency, overheating, internal moisture or humidity, airtightness, insulation, and window installation. So I'm going to go through those. I'm going to do a little bit of repetition just in case some of you haven't listened to last month's blog. If you do want a copy of last month's blog, just flick me a message or DM me and I will send you a link to it. So I will touch a little bit about the background information to it so you can understand how the Passive House Standard, which is an international standard, sets targets and performance requirements to meet World Health Organization requirements for a healthy home. It also has a cap on the amount of energy that can be used in order to create that healthy home. So the Passive House Standard has been around since about 1992. It was developed by Wolfgang Feist in Germany. There's a lot of people that say Passive House only belongs in cold climates. I get a little kick out of this because in New Zealand we have a building code that focuses very heavily on heat loss. You don't worry about heat loss in a tropical climate, but the reality is Passive House can actually be built anywhere in the world. It's an international standard. It's a voluntary standard. The difference between that and our building code is that the building code is legal requirements. The Passive House Standard sits with energy performance. It doesn't sit with sustainable materials. So with the challenges that we're seeing with low embodied carbon in buildings, we're going to have to address that outside Passive House. So the Passive House Standard doesn't replace our building code. It is our building code actually uses a lot of standards like NZ 3604, which our Minister Chris Pink has been talking about a little bit. That is actually a New Zealand standard. So the Passive House is actually the same thing as that, excepting it's international. Okay, so we'll start with ventilation. The part of our New Zealand Building Code that deals with ventilation is called G4. And this sets out the minimum requirements for natural ventilation. And as I explained last month, we rely heavily on opening doors and windows for ventilation. We also have kitchen range hoods and bathroom extracts as part of the ventilation system. But there is a rule in our New Zealand Building Code that says that for every habitable room, that's a bedroom, a living room, a kitchen, for any one of those rooms that we're actually living in, not necessarily a bathroom, for any habitable room, we need to provide an opening area of 5% of the floor area of that room. So the World Health Organization says that in order to have healthy air in our homes, in our internal environments, we need to replace that air to an air change rate of 0.35 to 0.5 air changes per hour. What that means in layman's terms is that the entire volume of air in your home needs to be replaced every 3.5 hours, or every 2 hours if you're using 0.5. So that's a lot of volume, and our building code says just open doors and windows and that will happen. And as I touched on last month, there's some practical issues with this, is that we typically, due to human behavior, we don't open up our doors and windows really wide when we're cranking up the heating in the middle of winter. We generally don't sleep with our doors and windows wide open, and we close them and secure them when we're out during the day. So that ventilation doesn't actually happen consistently. It only happens when we're home. We need that to happen consistently. So studies have shown that we can only rely on our doors and windows in Auckland for about 10% of the year to adequately ventilate our spaces. And as I explained in last month's blog, studies have been done by a lady called Cara Rosemere, and she was monitoring carbon dioxide levels. And the reason why that's important is we breathe oxygen, we breathe out carbon dioxide. So we know if there's not enough ventilation in that space, our carbon dioxide levels will be quite high and unhealthily high. So how does Passive House ensure that this ventilation happens without relying on the building code assumptions of doors and windows? So the Passive House standard calls for a ventilation system to be designed. I just want to sort of, I might get in trouble for saying this, bust a myth, but you can actually open up your doors and windows in a passive house. It's just that with this ventilation system, you don't have to in order to get those healthy levels of ventilation. So this ventilation system uses outside air. That's really, really important. It's not drawing air from your ceiling space. It's not drawing air through the cracks and gaps in your building envelope, as some ventilation systems say that they work. This takes fresh air from outside, it filters it, and it evenly distributes it around your home to what we call supply spaces, so areas where we pop in this fresh air. Then you will have extract spaces, typically like your bathroom and your kitchen areas, where you have a transfer of air through from the supply spaces through to the extract spaces, and that is extracted and then distributed back outside. So what we know is that we're getting fresh air from outside. We know that it's been filtered, and we also know that we're taking out that stale air, which will be loaded with moisture and is humid, and that also will have high carbon dioxide levels. It's referred to as a balance system, and the reason why that is because it creates a pressure within the internal environment to ensure that air moves from an area of higher pressure to an area of lower pressure. We watch the weather, we want to see if the wind is blowing, we look at how close the isobars are, and we look at air moving from an area of higher pressure to an area of lower pressure. The ventilation system operates on the same premise. So that's really important to know. That ventilation system happens continuously all the time. There is an unoccupied rate, there is an occupied rate for the typical amount of occupants that will be in a home, and there's a boost rate. So if you're having a party, you can still ensure that everyone's getting nice, healthy air to World Health Organization standards. So it works guaranteed, not just relying on that 10% of our windows opening and closing. The next part that Passive House addresses really well, that our building code makes massive assumptions about, is called energy efficiency. So this is the part of the code that's called H1. And last month I explained a little bit about insulation and how we rely so heavily on insulation levels in our building code to create energy efficiency. In February, our consultation closed for submissions on H1, energy efficiency, because our government is wanting to make some changes to that. So you might have heard a lot about H1 just recently. So energy efficiency really is independent of our New Zealand Building Code, is about quantifying how much energy use a home needs for a prescribed performance level relative to the position, location, and orientation of a home and the design of that home, because different designs will offer different results of energy efficiency. So our insulation really does focus on heat transfer through building elements. So that is how quickly you can transfer heat from one side of an element to the other side of it. So the fluffy stuff, what it does is it slows down the transfer of that heat. Okay, so that's why it works really, really well. As an insulating material, it slows down the transfer of heat from inside to outside on a cold winter's night. It also can slow down the transfer of heat from outside to inside on a really hot summer's day. But this doesn't actually quantify what our power bill is going to be like. It has an impact on our power bill, but it's not the whole part of it. So last month I explained that there's 3 compliance ways under our New Zealand Building Code under energy efficiency. And two of them are acceptable solutions. They focus only on heat loss. They focus only on insulation levels and assumptions about heat loss. And they don't focus very firmly on the location of the building. We have 6 climate zones divided through New Zealand, but within those climate zones, there's a huge variation. And within those variations, also, various designs are going to operate differently. So there is a third method. It's a verification method. It's called energy modeling. And this calculates heat losses and heat gains specific to that design, specific to that climate data for that project's location, for its orientation, with targeted temperature ranges. Our New Zealand building code just says our buildings can't drop below 16 degrees Celsius and there's no maximum temperature. So this sets a temperature range to achieve that energy, to quantify that energy use. And our passive house standard calls for a temperature range between 18 and 22 degrees Celsius. And as I just mentioned, our building code says legally you can't drop below 16 degrees Celsius, although there's no way to test for that, and there's no way that you have to prove that. It's just assumed in the calculations somewhere that some scientist has gone off and given a prescribed way of doing things for designers to tick the box when they go to council, and there's no maximum. So the energy modeling is really site-specific, using climate data. It uses NIWA climate data, and it's updated regularly so that we're using the latest, because we do know that our weather patterns are changing. So the passive house standard is actually energy modeling. And as I said, it uses NIWA climate data. And so we've got an energy cap within the passive house standard that says that you can use no more than 15 kilowatt hours per square meter annum to heat, cool, and operate your home. So what you have to do using the passive house standard is you have to adjust the design to make sure that it meets those criteria so that when it's built and occupied, it actually performs that way. That's not mandatory in our New Zealand building code. So that energy cap, as I said, is 15 kilowatt hours per square meter annum. Brands did some testing around code-compliant homes to see what the energy use would be to keep a code-compliant home, so just a barely legal minimum home, typical in New Zealand, how much energy that would take to keep that at a constant temperature between 18 and 22 degrees Celsius, which is the World Health Organization's recommendations for a healthy indoor temperature range. And that value was about 120 kilowatt hours per square meter annum. So the passive house standard dramatically reduces the amount of energy that you use, which is why the power bills are so low. But it also dramatically improves the comfort levels that you're experiencing for that energy use. And our code compliant homes are at the way extremes of that, negatively. So the passive house standard also uses a heat recovery ventilation system. So this is called a mechanical heat recovery ventilation system. It's not just a heat recovery ventilation system. And that means that all the heat that can be recycled in your internal environment is transferred to that dry, fresh air. It's not just recycling heat into your house. The reason why we can't do that is because if we're just recycling that heat, we're also recycling all of the moisture within your home. We're also recycling all of the carbon dioxide in your home. So that mechanical heat recovery ventilation unit can recycle heat. In a passive house, it has to recycle a minimum of 75% of the heat in the house during the cooler months, which is how we lower some of those power bills. And so that's a minimum. And that it cannot be recycling heat and moisture and carbon dioxide. It has to be recycling heat to dry, fresh air. And so healthy air. Also, dry air is a lot easier and cheaper and quicker to heat than humid air. So there's an efficiency within that system already. So the New Zealand Building Code cannot actually quantify the energy that's required for a healthy home. It assumes it, and it doesn't actually address it. And it calls on very high power bills from people who are living in these spaces. It doesn't give any consideration to you, the homeowner, who has to afford to live in that house. The third area that I highlighted as being a gap in our New Zealand Building Code is overheating. You would have heard a lot about overheating just recently too. And this is all related. All of these things are kind of have an impact, because remember, our house is a machine for living in. What you change in one part of your house and in one part of the construction is going to have an impact on the performance in another part of the house. It's all related, just like all the parts of a car work together for the car to be drivable. The same thing in a home. So We're still reasonably warm here in New Zealand. A lot of us are experiencing spaces that are overheating. There's a man down in Christchurch who said that his internal environment is getting to 50 degrees Celsius. So legally, a code-compliant home, it can overheat. You might have heard me say it's legal to fry a baby in New Zealand. Our body temperature is 38 degrees Celsius, 37.8. We know that when babies' body's temperature get close to 38 degrees Celsius, they say you need to take this child to hospital. So you imagine what a space that's 38 degrees Celsius is doing to our children, let alone our own bodies. So the only way to stop overheating in your house is to know what solar gains are coming into your space. So some people have said, oh, insulation causes overheating. That's not really true. It just slows down heat transfer. So if you've got a really, really hot interior, it's going to slow losing that heat out through the insulated elements. But the elements that actually cause our buildings to overheat are the windows, because glass is where we get solar gains in, right? It's also where we get solar losses. So that's where our greatest solar transfer is. So if we don't know the impact of where our windows are facing, how large they are, what material they're made out of, what the glass is made out of, and how they're installed, we're not actually going to know what the impact of the sun is going to be on that design. So we have these acceptable solutions for energy efficiency in our building code that just focuses on insulation. We don't actually legally have to quantify the solar gains, which is why you're seeing designs overheat. We can use shading to stop the sun from reaching our internal spaces in summer, and that is one of the philosophies or one of the design approaches of Passive House. So you want to make sure that you've got adjustable shading, and you want to know what the impact of that shading is, because obviously we want to hit those solar gains in winter because that lowers our heating bills, but we definitely don't want them in summer. Some people think that if you put internal blinds or you close your curtains, that's going to stop your space from overheating. The minute that solar gain has come in past the glass, you now have to deal with it in your internal environment. So the trick is to stop it from getting to your internal environment before you have to then deal with it. So prevention is better than cure. I do want to make a quick distinction here. Sorry, this was a last minute note. There is a big difference between air conditioning and ventilation, and this is important to deal with overheating. Lots of people are running out and putting air conditioners in their home, and I completely understand why. But an air conditioner and a heater simply conditions the temperature of the air. So if you have got an internal environment and you're using an air conditioner, all you're doing is cooling that same air. You're not removing carbon dioxide. You're not adjusting the humidity levels of it. And just to remind everybody about the water cycle that we learned in high school, about how you get rain, you have warm, humid air that rises, it reaches an altitude, it cools, it condensates, and then it drops. So if we've got quite humid internal environments in the hot summer months, and we start conditioning that air, we're going to start to cause condensation within our internal spaces, and that's not great because we want dry homes. So that's just something to be aware of. If you're trying to mitigate overheating simply with air conditioning, you need to pair air conditioning with ventilation. So the Passive House standard uses the energy modeling to assess where the overheating is happening. It has these strict energy criteria, so you have to adjust your design to make sure that you're not having to deal with overheating. You don't want it to go over 22 degrees Celsius. As I said, our building code says it can go as hot as it likes. And so we're constantly adjusting the design in the concept stages to make sure that we're going to be in line with those targets, because otherwise you can't become certified Passive House. And we need to prove that. So adjusting window orientation, window sizes, all of that, considering the window installation, knowing all of that stuff, that once it's installed is now going to perform, because it's really expensive to change those things once your building is constructed. So that's the big thing about overheating, and the big way that Passive House is actually plugging the gap that our New Zealand Building Code isn't even addressing. The fourth gap in our New Zealand Building Code is internal moisture. The part that deals with this is E2. There's also a part that is called interior environment that deals with it. The part of the code that deals with internal moisture, or E2, calls for kitchen range hoods and bathroom extracts. So that's why it's It's part of the healthy home standards for rental homes. You have to have a bathroom extract and a kitchen range hood, and it's mandatory for new build homes. You have to provide the fan speeds to the New Zealand a building consent authority in your building consent documentation if you're an architect or an architectural designer to satisfy and tick that box. However, the issue with the range hoods and the extract systems is they're only in two rooms of the house. They're not dealing with supply of dry air. They're just dealing with extract of humid air. They're reliant on human behavior, so they're intermittent. We only turn them on when we're cooking, and we only turn them on when we're having a shower, and that is if we remember to turn them on. So they're not actually guaranteed to work. The other thing too is that while you've got these fan speeds of 50 litres per second in your kitchen range hoods and 25 litres per second in your bathrooms, if the ducting from the fan to the outside is not an efficient layout, those fans are working really, really hard and not performing to the assumption of the levels that they're actually achieving. So they're not actually drying your space to what it says on the tin. So Passive House addresses this by calling for that mechanical heat recovery ventilation unit. So it's actually got this consistent ventilation system. So as I said, it's removing humid air. It's also removing carbon dioxide continuously with those three functions: unoccupied, occupied, and boost. It means that we can transfer warm recycled heat in the winter months with the heat recovery function of this ventilation unit to dry, colder air. Dry, colder air is easier to heat. It's also dry, which means that we're not breathing in humid air. Humid air is actually what's causing a lot of respiratory issues. New Zealand has the highest asthma rate in the developed world. Our child asthma rate is terrible. We're world champions at it. And a lot of it is being caused by our children growing up in damp homes and breathing in this humid air. And this is coupled again with the ventilation, the assumption of our doors and windows. But this is, I'm specifically trying to say, to internal moisture. As I said, they're all kind of related. So constant ventilation, it means that we can control the humidity. In summer, you can boost that ventilation system to move humid air out of your space really, really quickly. We also give off about 3 litres of moisture a day with our breath. If you are aware of having condensation on your windows in your bedroom in the middle of winter, that condensation is coming from our breath. It's not solved by double glazing. It's solved by having adequate air changes per hour to remove that humid air. And of course, in the middle of winter, we have all our doors and windows shut as much as we can because we're trying to conserve heat in our spaces. So that ventilation system within the Passive House not only means that we get fresh air to breathe, it also means that we're removing humid air and we're addressing the humidity levels and the internal moisture issues that are happening in our house. Internal moisture issues are also created by the lack of an airtightness strategy. So the fifth gap in our New Zealand Building Code that I highlighted last month is airtightness. So there's no requirements really for airtightness. We have a section in our code called E3, which is the internal moisture. We have H1, which is energy efficiency, and airtightness actually affects both. Our code-compliant homes, our new code-compliant homes, is using quite airtight joinery and quite airtight construction details. However, they're not up to the Passive House airtightness standard. And the thing about airtightness is if it's done accidentally, we can actually have silent issues that we're not aware of. Airtightness is one of those things that you have to get done right. And if you don't get it right, you create a big issue. So the airtightness layer in a Passive House is intentional. It's designed into it. It's also tested on site with a blower door test. This is what it does for healthy homes, is it stops any air moving through our walls, ceilings, and floors. It's sealed up at all the cracks and the gaps. Some of those heat recovery ventilation, the heat recovery ventilation system salespeople will often tell you, especially if you're retrofitting one, we use the gaps and the cracks to pull air in. You don't want any air moving through those gaps and the cracks, because if we've got warm, humid air, even outside or inside, and it's moving through your construction system, and there happens to be a surface that it hits that is cool enough for it to condense, you're going to end up with condensation in your wall, floor, and roof elements that you didn't even know was there. and it's going to cause rot and mold issues out of sight. Timber is an organic material, so if it gets moist, you're going to get mold and rot in it. And you only really discover this when it's a really expensive repair. We knew this with the leaky building saga that we had in New Zealand in the 2000s. That was caused by rot and mold happening in places where we couldn't see. That happens when you get water or moisture egress into your structural elements that you can't see. So an airtightness membrane stops any humid internal air from going into those spaces where we can't see it. Our weather tightness layer on the outside of our new build homes is really good at stopping water and water vapor from getting into that space too. But both those membranes allow water vapor to go out of them, because our timber can have up to 20% moisture content when we close it all in, and you want that moisture to slowly come out, or if there's any moisture in there, you want it to be able to move out of that space, but it doesn't allow water to go into that space. So as I said, the Passive House Standard calls for a blow door test. You have to be intentional about the air tightness strategy that you have in the design, and then you test it. We typically do 2 tests. One is before you close everything up with internal lining, so you can identify any gaps in the air tightness layer so that you can then remedy them and seal them up. And then you have the certification one, which is your final result. So how this works is that you close up your doors and your windows. You put a blower door fan into one of the doors that seals all up, and you have all of these sensors, and you pressurize the building. So you cannot have an air change rate of greater than 0.6 air changes per hour at 50 kilopascals in a passive house. And that sounds awfully technical. But what that means is you're testing the leakage of air out of that space. Now, if we were to test a code-compliant home to see what that air change rate is, we're sitting around between 4 and 6 air changes for most of our homes in New Zealand. So that's kind of accidental air tightness versus an intentional. You can have no more than 0.6 air changes per hour at 50 kilopascals per hour. And that is to stop that interstitial condensation. The fifth area that our New Zealand Building Code is not doing as well as the Passive House Standard is doing is insulation. And I know that we've talked about energy efficiency and our reliance on insulation levels, but there's a lot of assumptions in those acceptable solutions about timber content. We build a lot of our homes here out of timber. Timber is a much better thermally performing material than steel. But just banging a hole of timber into the wall means that we're compromising the performance of that insulation. So a thermal bridge is a weak spot in our insulation level. And the challenge is that in New Zealand, our wall and floor and ceiling elements are typically the space where you've got insulation, you've got structure, and you've got services, and they're all shared in the same space. So that means that we have your structure, you have your services, your insulation just gets what is left out. So every time we have a stud in a wall, or we have a hope of timber in an external corner, or we have a wall-to-floor junction, we've got a lot more timber than insulation. And we want insulation to be as continuous as possible, because that way it's as effective as possible. So understanding where those thermal bridges are and quantifying them is really, really important. We have to model that in Passive House, and we have to quantify the energy loss through, or the heat loss or the heat gains through those junctions, so that we know where we have to compensate elsewhere to make up for that, because the house is a whole thing. We're wanting the whole thing to perform to those targets. So we want to understand what those are doing, and we design them out as much as possible so that we're obviously then not relying on more expense and insulation in order to get the performance. Whereas if we can remove some timber that's not needed to be there, that just seems like a smarter idea. So that's what happens when you are designing to the Passive House Standard. We also want to make sure that those junctions, because thermally they're weaker than the spaces that have got lots of insulation in them, we want to make sure that they're not going to be surfaces where you're going to have condensation against them, and then you're going to have mold or rot forming on those surfaces. And so all of those junctions are modeled to get what they call as an FRSI factor, which is a surface temperature factor, to ensure that we're not going to get mold on the skirtings, or we're not going to have mold behind wardrobes, etc. We don't want mold anywhere in this house, because mold, again, is one of the causes of respiratory illnesses. So our New Zealand Building Code doesn't really consider thermal bridges. It assumes that we have got 12% timber content in our wall, floor, and ceiling elements, and therefore that we've got 12% of structure and 88% theoretically percent of insulation in all of those areas, and then that's the generic assumption that's applied to all of those insulation value requirements to tick the box. But studies have actually been taken. A study was done by Beacon Pathways on actual building sites and actual homes, and quantifying the amount of timber that is going into our wall, floor, and roof elements. And they found that 12% that is assumed in our New Zealand building code is incorrect. The amount of timber that's actually sharing our insulation layer is closer to 34%. So that means that the amount of insulation that we're putting into our wall, floor, and ceiling elements is actually not 88% of that element, it's 66% of that element. So even the assumptions that have been made in our New Zealand building code are failing. So our actual built homes are performing way worse than even the minimums that are set out in our code. So the passive house standard, as I said, calls for those weak spots. We calculate it, you use building science, you use data, and then you compensate for them elsewhere if they're unavoidable, and you use smart, clever designs to ensure that you can design them out so that, prevention is better than cure. The last element that I highlighted as being a shortcoming in our New Zealand building code is window installation. So, as I said, our building code is treated generally as a design guide, and the one space where this is very, very evident is in a clause or a section called E2, E2AS1. So it's external moisture. E2AS1 underwent a massive revamp after our leaky building saga, and everyone scrambled to get better weatherproofing details, which is not a bad thing. However, the strategy for getting those better weatherproofing details was to hang the aluminium joinery over the cladding and over a drainage cavity. Now, because most of those leaky junctions were at cladding junctions, most of those leaky issues were at cladding junctions and around doors and windows. Now, because there's this prescribed set of details in the building code that are acceptable solutions, a lot of manufacturers use those details for their manufacturing details and for their warranties. A lot of architects and designers rely on them because it's in the code. So insurance risks, etc., is a lot easier. It's a lot lower, and it does on the surface make sound business sense. But what it's not doing is actually producing a quality result for our clients and for home occupiers. So a couple of issues. First of all, it's heavily focused around aluminium. Aluminium is a poor performing material. We use it in our pots and pans. We use steel in our pots and pans because metal's a really good conductor of heat. Why would we be using a good conductor of heat when we're trying to install an upspec or add to our insulation to stop heat loss? Why would we be putting those elements using that material? So staying away from metals is a really good idea for energy efficiency and for healthy buildings. So one, it focuses on aluminium, and two, it hangs it outside the cladding line, which means that you've got a clear heat path for heat to track through. So it becomes a very, very weak junction thermally. So what we want to do, and what Passive House calls for, is we want to recess those doors and windows into the insulation line so that we can make that installation detail as high performance as possible. Also, we want to start using better performance materials. Aluminium has a thermal conductivity of 160. UPVC has a thermal conductivity of 0.18, and timber has a thermal conductivity of 0.13. Now, I know people have a thing about UPVC. I covered this in January's blog where I touched on Stark UPVC joinery. They recessed their joinery, their UPVC joinery. We now use UPVC, which is the same material as the Marley spouting, and it's unplasticized, so it's actually UV stable. So the days of using that really poor performing UV material is gone. And also we're seeing that because our minimum window requirements have been raised up with our minimum standards in the building code, we're starting to see UPVC and thermally broken aluminium becoming price competitive because we're having to use higher performance glass in the aluminium frames to compensate for the poor performance of the aluminium frames, whereas we can use a lower performance glass to achieve those minimums with UPVC because the frame is a better performing frame. Another issue with using aluminium joinery is because it's a good conductor of heat, they tend to be the coolest surface. So if we're wanting to stop any surfaces within the interior of our environments from having condensation up against them, so that then that creates mold issues, we want to have materials that are quite thermally stable, and aluminium's not. So if we're going to invest in better performing windows, we want a better performing installation detail. We also want to know how that installation detail is performing, so we can get bang for our buck. I'm going to quote Benji Simons from Stark here. He says you can take a high performing unit and completely waste its value by putting it into a poor performing installation. So Passive House calls for that, and it quantifies it, and there's energy calculations and thermal calculations around it. So that we know that the investment in better performance, we know we quantify it, and we know where we're making it. So that is the 7 ways that the Passive House Standard actually delivers healthy, comfortable, energy efficient homes, rather than just assuming it, and how it fills the gaps that those assumptions or not considerations within our New Zealand building code. Most of our new homes, particularly those ones built by housing companies, are built to the minimum standards of the building code. With cost being used as an excuse, I'm not saying that you should spend a huge amount of money on your house and mortgage yourself untenably. However, I think that there really is a better way to create our homes, and that cost is used often as a barrier to exploring other ways of doing this better. And at the end of the day, our homes are our largest financial investment that we make in our lifetimes. We spend years paying off a mortgage. They're also the space that we spend most of our time in, and they're the space that support our family's health. So it really is worth investing in getting it right. Our general public, which is probably some of you that are listening to this, really believe that a co-compliant home is a quality one, not just a legal one. So when we stop viewing standards like the Passive House Standard as an addition, as a nice to have, as elitist or expensive, we are still going to continue to create homes that overheat, that have internal humidity issues, that are creating internal environments that are not good for respiratory illnesses, that are not good for our health, that are not good for our own body temperature requirements. And we're still going to make assumptions that all of this additional investment in better building products is actually delivering the performance and delivering the benefit to us that we think they are, if we're not quantifying it and if we're not designing to a standard that is streamlined to that. We're also not going to create energy efficiency in our homes if we're not energy modeling, and we're not going to create energy efficiency in our homes if we're not considering that and capping that in our designs. If we're just going, oh yeah, she'll be right. We're very good here in New Zealand. Yeah, don't worry, mate, she'll be right. So I really do believe you deserve a healthy, comfortable, energy efficient home to live in. And on top of this, if we're going to start investing in PV panels and smart meters like Basis has got to generate electricity, the less energy your home needs to operate, the less PV panels you need to put up on your roof. So therefore, the lower the cost is to not only generate your own energy, but to invest in the systems to generate your own energy. So I hope this helps you understand Passive House just a little bit more. As I said, next month I'll be talking about Homestar and how this plugs the 7 gaps in our building code. I'll also explain how Homestar is complementary to Passive House. I sometimes get asked Homestar or Passive House, which one? They're actually different. There are overlaps, but they're not exactly the same. I think we like things to be really, really simple, but they actually work in tandem with each other. So follow me on Facebook, Instagram, TikTok, or LinkedIn. Every day I just give daily snippets and little nuggets that I've covered in here, but I also just release them out there in a different way. So you can get your little daily dose of education on how to build better. And if you're watching this on YouTube, please like, share, or subscribe the channel. It is my mission to educate people on how to build better, because it's my mission to create healthy, comfortable, energy efficient homes for everyday people right around the world. So I would appreciate that. It really helps the work that I do.